Hello students, in today's lecture we are going to learn about mechanical properties of fluids. In this lecture we are going to cover NCERT section 9.5 to 9.6.5 and we will also solve an example 9.8. This is our disclaimer. Learning objectives. By the end of this lecture, you will be able to understand viscosity, surface tension, and related fluid properties through theoretical concepts and mathematical relationships. Apply principles of fluid mechanics to analyze real world examples like capillary action, droplet formation, and fluid flow in pipes. So, students, in today's lecture, we will cover first 9.5 viscosity, then example 9.8, then 9.5.1 Stokes law, then 9.6 surface tension, 9.6.1 surface energy, then surface energy and surface tension, then 9.6.3 angle of contact, then 9.6.4 drops and bubbles, and last 9.6.5 capillary rise. All right. So, students, let's start with viscosity. Viscosity is a fundamental property of fluids that measures their resistance to flow. Viscosity arises when there is relative motion between layers of fluid. Alright, it means measures their resistance to flow. Viscosity arises when there is a relative motion between layers of fluids. Fluids with high viscosity like honey or syrup flow slowly due to high internal friction, while low viscosity fluids such as water flow easily and quickly. This internal friction arises from the fluid's molecular structure and uh, how its layers move relative to each other when subjected to stress. While low viscosity fluids such as water flow easily and quickly. This internal friction arises from the fluid's molecular structure and how its layers move relative to each other when subjected to stress. Students, now we are going to focusing on how temperature affects the viscosity of fluids. We know viscosity is a measure of how much a fluid resists flowing. First, we know viscosity of liquids decreases rapidly with an increase in temperature. Alright, this means that when you heat a liquid like warming up honey, it flows much more easily. The molecules move faster and can slide past each other more easily, so the liquids becomes less thick. Viscosity of gases increases with an increase in temperature. As gas molecules move faster, they collide more often, which increases the internal friction and makes the gas slightly more resistant to flow. For example, warm air is just a bit more viscous than cold air. So, heating a liquid makes it flow more easily, but Heating a gas makes it flow a bit more slowly. This difference is important in real world situations like engine oils or airflow in ventilation systems. Remember, temperature affects liquids and gases in opposite ways when it comes to viscosity. Now, we will discuss the effects uh, or learn how viscosity affects fluids, flow, and behavior. So, let's consider a simple setup. Imagine a layer of oil trapped between two gaseous plates, as shown in the figure 9.12. A liquid of a layer of liquid sandwiched between two parallel glass plates, in which the lower plate is fixed and upper one is moving to the right with velocity v. All right. So the lower plate is fixed. All right, in place, while the upper plate can move. This setup helps us visualize how the fluid behaves when a force is applied. All right. Here, the oil is sandwiched between the plates. This is a classic way to study viscosity in the tab. Now, focus on what happens when we move the top plate to right at a constant speed. Alright, while the bottom plate still stays still. Alright, the oil in contact with the moving plate tries to move along with it, while the oil near the fixed plate stays put. This creates a velocity difference within the fluid, which is exactly what viscosity acts to resist. So, uh, imagine you have a plate moving over a layer of oil and then you replace the oil with the honey. You will notice that you need to push much harder to move the plate at the same speed when using honey. This is a direct observation of how different fluids resist motion. So, this tells us that honey is more viscous than oil. In other words, honey has a higher viscosity, which means it resists flow more strongly. Viscosity is a key property that determines how thick or sticky a fluid feels when you try to move something through it. Alright, so the fluid that touches a surface actually moves at the same speed as that surface. This is called no slip condition. For example, if the bottom surface is fixed, the fluid touching it does not move at all, while the fluid touching a moving plate moves with the plate. So the layer of liquid in contact with the top moving surface travels at a velocity v, while the layer touching the fixed bottom surface stays still. This creates a gradient of velocities from the bottom to the top. It's important to remember that the velocity changes smoothly from one layer to next. If we look at all the layers in between, their velocity increases evenly from 0 at the bottom to v at the top. This means each layer moves a bit faster than the one below it. This gradual change in velocity across fluid is a key feature of viscous flow. For any layer of fluid, the layer above it tries to drag it forward, while the layer below tries to slow it down. This tug of war between layers creates an internal friction or viscous force within the fluid. It's this internal friction that we measure as viscosity. This internal friction results in a force between the layers. The upper layer pulls the lower one forward and the lower layer pulls the upper one back. This is why moving one layer affects the motion of the others and why more viscous fluids are harder to move. This type of flow is known as laminar. Alright. Now, coefficient of viscosity. So let's start by defining the coefficient of viscosity. It's often represented by Greek letter eta. The coefficient of viscosity is the ratio of the shearing stress applied to a fluid to the rate at which the fluid is deformed, or the strain rate. In simple terms, it tells us how much force is needed to make a fluid flow at a certain rate. Now, eta equal to, if we talk about mathematically, eta equal to force upon area divided by velocity upon L, which is equal to, when we rearranging the terms, you will be get eta equal to FL divided by VA. And if we talk about the SI units, so it will be PI. Alright. So this unit is not a commonly used in everyday situations, but it's a important to know for scientific work. Its other units is Pascal second. These are equivalent ways to express viscosity in SI systems. Dimensional formula M L inverse T inverse. This tells us how viscosity relates to the fundamental physical quantities of mass, length, and time. Understanding dimensions helps us check if our equations make sense and can be useful for unit conversions. Generally, thin liquid like water, alcohol, etc. are less viscous than thick liquids like coal, tar, blood, glycerine, etc. This difference is why honey pours slowly while water pours quickly. Example 9.8. A metal block of area 0.10 meter square is connected to a 0.010 kg mass via a string that passes over an ideal pulley, considered massless and frictionless, as in figure shown here. So, a liquid with a film thickness 0.30 mm is placed between the block and the table. When released, the block moves to the right with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the liquid. Alright, let's see the solution. So let's start by listing all the information given in the problem. Area of metal block A equal to 0.10 meter square. Mass connected to string M equal to 0.010 kg. Film thickness H equal to 0.30 mm, which is equal to 3.0 into 10 raised to the power minus 4 meter. Constant velocity V equal to 0.085 meter per second. Acceleration due to gravity 9.8 meter per second square. Now, first let's think about why the block moves to the right. It's because the tension in the string caused by the hanging mass pulls the block. This tension is what initiates the motion, and since the block moves at a constant speed, the forces must be balanced. So the tension which we call T is equal in magnitude to the weight of the hanging mass. Remember, weight is just mass times acceleration due to gravity. So T equal to M into G. Thus, the shear force F equal to T is equal to mg. Here F is the force in newtons, M is the mass in kilograms, and g is the acceleration due to gravity, which is about 9.8 meter per second squared. This formula gives us the exact value of force applied. F equal to 0.010 kg into 9.8 meter per second square. So when we calculate this, we get F equal to 9.8 into 10 raised to the power minus 2 Newton. Alright. So let's find the shear stress on the fluid. So shear stress is defined as force divided by area. So we use the formula shear stress is equal to F by A, which is equal to 9.8 into 10 raised to the power minus 2 divided by 0.10 Newton meter square. Alright. Now strain rate is equal to V by L is equal to 0.085 divided by 0.30 into 10 raised to the power minus 3. So H equal to stress upon strain rate per second. H equal to, put the values, 9.8 into 10 raised to the power minus 2 Newton into 0.30 into 10 raised to the power minus 3 meter divided by 0.085 meter per second into 0.10 meter square. So finally, we find that the coefficient of viscosity is 3.46 into 10 raised to the power minus 3 Pascal second. Alright. Now, let's start by looking at Stokes' law. This law tells us about the viscous drag force, which is the resistance a small round object feels when moving through a thick fluid. This drag force depends on three things: the radius of the sphere, the viscosity of the fluid, and how fast the sphere is moving. Think of how it's harder to move your hand quickly through honey than through water. Mathematically, F equal to 6 pi eta AV. Right? Viscous drag force F depends on fluid viscosity eta and sphere radius. Alright. Now, let's start by considering a falling raindrop. This is a great real world example to visualize how forces act on an object moving through a fluid like air. So, at first, the raindrop accelerates downwards due to gravity. Gravity is pulling it towards the earth, just like any other object in free fall. This initial acceleration is similar to what you would see if you drop a stone from a height. Velocity increase leads to increased retarding force. This force is called viscous drag, and it is increased as velocity of the raindrop increases. When viscous force plus buoyant force equals gravitational force, acceleration becomes zero. When this balance is reached, the raindrop moves at a constant speed called terminal velocity. This means it continues to fall, but its speed does not increase any further. Terminal velocity is an important concept because it explains why raindrops don't become dangerous projectiles as they fall. At equilibrium, we can calculate the terminal velocity using a specific formula. So 6 pi eta a vt is equal to 4 pi divided by 3 a cube into rho minus sigma into g, where rho and sigma are mass densities of sphere and the fluid respectively. Vt equal to 2a square into rho minus sigma into g divided by 9 eta. Now, Terminal velocity depends on first square of the sphere's radius, inversely on fluid velocity, difference in densities between sphere and fluid. Alright, so definition of surface tension. So let's define what surface tension actually is. This is an important term in fluid mechanics, and understanding its definition will help us see why liquids behave the way they do at their surfaces. Surface tension is defined as the force per unit length acting perpendicular to any line drawn on the surface of a liquid. In other words, if you imagine drawing a line on the surface, surface tension is the force that acts at the right angles to that line, trying to minimize the. This is why water beads upon a surface. So we can express surface tension with the simple formula gamma equal to F by L, or we can say F by L, where uh, gamma is surface tension, F is equal to force acting on the length L, length of the line on the surface. Alright, L is the length of the line on the surface. SI unit Newton per meter, or uh, joule per meter square. Now, surface energy. So let's define surface energy. Surface energy is the extra potential energy that molecules have at the surface of a liquid compared to those inside the liquid. This happens because molecules at the surface are not surrounded by other liquid molecules on all sides, so they experience different forces. In simple terms, surface energy is the energy needed to create a new surface by breaking the bonds between molecules. To put it another way, surface energy is the work done per unit area to increase the surface area of a liquid. For example, if you stretch a soap film, you have to do work to make it larger, and that work per square meter is the surface energy. Alright, materials with high surface energy are easily weighted like water, while those with low surface energy, such as hydrocarbons, cause liquids to bead up characteristic non-stick surfaces. This explains why water forms droplets on a waxed car but spreads out on a clean glass. Now, let's focus on why a liquid stays together. It's because the molecules inside the liquid attract each other. These are called cohesive forces. Imagine water droplets forming on a leaf. That's the result of these molecular attractions holding the liquid together. This attraction is what keeps the liquid from just flying apart. So consider what happens to a molecule that's deep inside the liquid. It's pulled equally in all directions by the surrounding molecules, so the forces balance out. Take a look at the figure 9.14. A schematic picture of molecules in a liquid at the surface and the balance of forces. A molecule inside the liquid, forces on the molecule due to others are shown. Direction of arrows indicates attraction of repulsion. Alright. B same for a molecule at a surface, and C balance of attractive A and repulsive R forces. Now, attraction results in a negative potential energy for the molecule, which depends on the number and distribution of molecules around the chosen one. Alright. But even though individual molecules might have different neighbors, on average, the potential energy for all molecules in the liquid is same. This means that overall the energy landscape is balanced throughout the liquid. It's important to remember that these averages helps us predict the liquid's behavior as a whole, not just for single molecules. This idea is supported by the fact that it takes a lot of energy to completely separate all the molecules in a fluid. Like when we evaporate water, the heat of evaporation is the energy needed to break these attractions and turn the liquid into vapor. For example, uh, to evaporate 1 kilogram of water at 100 degrees Celsius, we need about 2.26 million joules of energy. This shows just how strong the molecular attraction are in a liquid. Now, when the surface area of a liquid increases, work must done against the cohesive forces between the molecules. Alright. So take a look at the diagram 9.14. Schematic picture of molecules in a liquid at the surface and balance of the forces. Alright. So here inside the liquid, molecules are pulled equally in all directions, but at the surface the forces are unbalanced. This is why surface molecules behave differently. Think about how water forms droplets on a leaf. This is due to these surface forces. The work we do to increase the surface area does not just disappear. It gets stored as surface energy. Surface energy is the extra energy that surface molecules have compared to those inside the liquid. This explains why liquids tend to minimize their surface area, forming shapes like spheres. 9.6.2 Surface energy and surface tension. Let's look at this example. Imagine we have a thin film of liquid held by a frame and we move the bar a small distance to stretch the film. Look at the figure 9.15, stretching a film. A, a film in equilibrium. B, the film stretched an extra distance. The film goes from its original position to slightly stretched one. This setup helps us visualize how surface tension works in practice. When we stretch the film, its surface area increases. This means we have added energy to the system because it takes work to increase the area against the internal forces holding the molecules together. Think of it like stretching a rubber band. It resists being stretched and you have to do work to pull it apart. Let this internal force be F. The work done by the applied force is F dot D is equal to D. From conservation of energy, this is stored as additional energy in the film. If the surface energy per unit area is S and the uh, extra area created is 2 times D times L, where L is the length of the bar, then the total extra energy is S into 2dl. Alright. So a film has two sides and the liquid in between. So there are two surface and the extra energy is S into 2dl is equal to Ft. So S is equal to Fd divided by 2dl is equal to F by 2l. This quantity S is the magnitude of surface tension. Alright. It is equal to the surface energy per unit area of the liquid interface and is also equal to the force per unit length exerted by the fluid on the movable bar. So the relationship between surface energy and surface tension gives us deep insight into the molecular behavior at the surface of liquids. Understanding this connection helps explain why surface phenomena like the formation of droplets or bubbles occur. Now, Let's start by looking at how a fluid interacts with a solid surface. A fluid will stick to a solid if the energy needed to keep the fluid and solid together is less than the combined energies of the solid with the air and the fluid with air. In simple terms, uh, if the fluid likes the solid more than it likes the being next to air, it will spread out and stick to the solid. This means there is an attraction between the solid surface and the liquid. For example, water tends to climb up clean glasses because the attraction between water molecules and glasses is strong. This attraction is what leads to phenomena like capillary motion action. It can be directly measured experimentally. A flat vertical glass plate below which a vessel of some liquids is kept forms one arm of the balance. Plate is balanced by the weights of the other side with its horizontal edge just over water. So we slowly raise the vessel until the liquid just touches the glass plate at this point. So surface tension pulls to plate down slightly. This pull is due to the cohesive forces at the liquid's surface and it's what we are aiming to measure. Weights are added till the plate just clears water. Now, suppose the additional weights required is W. Alright, so take a look at this diagram 9.16 measuring surface tension. It shows a typical experimental setup for measuring surface tension. The plate partially immersed in the liquid and the weights being added. This visual helps us connect the concept to a real experiment, making it easier to understand how surface tension is measured in practice. Now let's talk about how we actually calculate the surface tension from this experiment. The surface tension at the liquid-air interface is what we are interested in. We will use the measurements from our setup to find its value. The formula for surface tension is in this case is S is equal to W divided by 12 is equal to mg divided by 12, where m is the extra mass and L is the length of the plate is. The subscript La emphasizes the fact that the liquid-air interface tension is involved. This distinction is important because surface tension can be different at different interfaces. 9.6.3 Angle of contact. First, let's look at the definition. The contact angle is a specific angle formed at the point where the liquid surface meets a solid surface. It's important to know exactly what this angle represents before we discuss its effect. The angle of contact is the angle between the tangent to the liquid surface and the solid surface, and we always measure it through the liquid. Alright. For example, if you imagine a drop of water sitting on a leaf, the angle is measured inside the water at the point where it touches the leaf. This angle helps us understand how much the liquid wets the surface. When a liquid touches a solid, the surface of the liquid near the edge forms a characteristic angle with the solid. This is called the contact angle or angle of contact. The size of this angle tells us whether the liquid will spread out or form droplets. For instance, a small contact angle means the liquid spreads, while a large angle means it forms beads or droplets. So let's look at a real world example. Water forms round droplets on a lotus leaf as shown in figure 9.17a, but it spreads out on a clean plastic plate as shown in figure 9.7b. This difference is due to the contact angle and the interaction between the water and the surfaces. Alright, so the shape of the drop changes depending on the surface. This is a direct result of the contact angle. Now Uh, let's look at the three interfacial tensions involved: liquid, air, and solid liquid. These are represented as SLA, SSA, and SSL. Interfacial tension is the force per unit length acting along the line where two phases meet, measured in Newton per meter. So look at figure 9.17. So in the image, how the notice that in the in this image the shape of the water drop changes depending on the surface, like a lotus leaf versus a plastic plate. This difference is due to how these tensions balance out. For example, if the liquid air tension is much higher than a solid liquid tension, the drop will bead up more, like on the lotus leaf. This concept helps uh, explain why some surfaces are water repellent while others are not. Now, at at the line of contact, the surface forces between the three media must be in equilibrium. From figure 9.17b, the following relationship is easily derived. So SL cos theta plus SL is equal to SA. The angle of contact is an obtuse angle if SA is greater than SLA. As in the case of water leaf interface, while it is an acute angle if SL is less than SLA. As in the case of water plastic interface. Now, when theta is an obtuse angle, then molecules of liquids are stressed strongly to themselves and weakly to those of solid. It costs a lot of energy to create a liquid solid surface, and liquid then does not wet the solid. This is what happens with water on a waxy or oily surface and with mercury on any surface. Now, uh, let's look at what happens when the molecules of the liquid are strongly attached to the molecules of solid. This strong attraction lowers the solid liquid surface tension, which we call SSL. When SSL goes down, the value of cos theta increases, so the contact angle theta gets smaller. All right. So on the lotus leaf, water forms a bead with large angle, but on the plastic plate, the drop spreads out more, showing a smaller angle. This difference is all about how the liquid and solid interact at the molecular level. In this situation, the contact angle theta is an acute angle, meaning it is less than 90 degrees. This tells us that the liquid is wetting the surface well. For example, butter on a clean glass or plastic forms a small angle and spreads out, showing strong attraction between the water and the surface. So this effect is even more obvious with liquids like kerosene oil, which spreads on almost any surface because the contact angle is very small. The key takeaway is that when the attraction between the liquid and the solid is strong, the liquid spreads out more. Now, soap, detergents, and dyeing substances are wetting agents. All right. So look at figure. Water forms different shapes of lotus leaf and the plastic plate. The shape of the drop depends on and contact angle, which is influenced by the interfacial tensions between the liquid, solid, and air. On the lotus leaf, the water beads up, showing a large contact angle, while on the plastic plate, it spreads more, showing a smaller angle. When they are added, the angle of contact becomes small so that these may penetrate well and become effective. Waterproofing agents, on the other hand, are added to create a large angle of contact between the waters and fibers. Now, suppose we have a spherical drop with radius r that is in equilibrium. So take a look at this diagram 9.18. So here the drop, cavity and bubble are all shown with the same radius r. This visual helps us compare different cases where surface tension plays a role. If its radius increased by delta r, the extra energy is 4 pi into r plus delta r whole square minus 4 pi r square into SLA is equal to 8 pi r into delta r into SLA. Now, if the drop is in equilibrium, this energy cost is balanced by the energy gain due to expansion under the pressure difference Pi minus P naught between the inside of the bubble and the outside. Work done is W equal to Pi minus P naught into 4 pi r square into delta r. Pi minus P naught is equal to 2 into SLA divided by r. In general, for a liquid gas interface, the convex side has a higher pressure than concave side. Remember, surface tension always tries to minimize the surface area, leading to these pressure differences. Example, an air bubble in a liquid would have higher pressure inside it. Look at figure 9.18b. Drop, cavity and bubble of radius r. A bubble of figure 9.18c differs from a drop and cavity. In this, it has two interfaces. Applying the above argument we have for a bubble, so Pi minus P naught equal to 4 into SLA divided by T. 9.6.5 capillary rise. Alright, let's examine a vertical capillary tube with a circular cross section and radius A that we insert into an open vessel of water. This setup is important because the narrowness of the tube allows us to clearly observe the effects of surface tension. So look at figure 9.19. Capillary rise. A schematic picture of narrow tube immersed water. B enlarged picture of near interface. The the angle contact between water and glasses is acute. So thus the surface of the water in the capillary is concave. Alright. This concave shape is a direct result of the adhesive forces between water and glass being stronger than the cohesive forces within the water itself. This that tells this curvature is what leads to the rise of water in the tube. This means that there is a pressure difference between the two sides of the top surfaces. Now, let's look at this diagram 9.19. It shows a narrow tube or capillary dipped into water, or water climbs up inside the tube forming a curved surface called the meniscus. This happens because the pressure difference between the inside and outside of the tube at the top surface, which is influenced by the surface tension. Here the formula for the pressure difference Pi minus P naught is equal to 2s divided by T is equal to 2s divided by A sec theta. So Pi minus P naught is equal to 2s divided by A cos theta. This thus the pressure of the water inside the tube just at the meniscus air water interface is less than the atmospheric pressure. Now let's focus on the figure 9.19. Here we have 2 points A and B. Alright, inside a narrow tube that's been dipped into water. So the water climbs up inside the tube forming a curved surface called a meniscus. This setup helps us analyze the forces and pressures involved in capillary rise. At this stage, it's important to realize that points A and B, which are at the same horizontal level in the liquid, must be at the same pressure. So P naught plus H rho G is equal to Pi equal to Pa, where rho is the density of water and H is called the capillary rise. Figure 9.19. Now, using equation 9.27 and 9.28, Pi minus P naught is equal to 2s by A cos theta. We have H rho g equal to Pi minus P naught equal to 2s cos theta divided by A. So capillary rise is due to surface tension. It's a larger for smaller a, and typical it is of the order of a few centimeter for fine capillaries. This effect is a crucial in many natural and technological processes like how plants draw water from the soil. Now, example, if A equal to 0.05 centimeter, using the value of surface tension of, for water, we find that H equal to 2s divided by rho g A. So substitute the values and you will be get H equal to 2.98 centimeter. Capillary action is the tendency of liquids to rise or fall in narrow tubes due to surface tension effects. Now let's summarize our lecture in some brief points. Viscosity represents internal friction in fluids defined by Newton's law F is equal to eta A into dV upon dy, where eta is the coefficient of viscosity. For flow in pipes, the flow rate is pi r raised to the power 4 P1 minus P2 divided by 8 eta. Surface tension, force per unit length acting on the liquid surface is due to molecular interactions. So surface energy is given by W equal to gamma into delta. Angle of contact. So angle between liquid surface and solid surface governed by Young's equation. Thank you for your attention. I hope this lesson was helpful. Thank you.